Hello, I'm Chinmay Tope, and this is my Physics 2212 Lab 3. So to introduce the main purpose of this lab is going to detail the interaction between magnetic objects. That's why I have magnetism, as well as assessing magnetic dipoles at different distances, as well as predicting using glow script the effect that distance has on the strength of a magnetic field. Following, we're also going to be looking at how to computationally model all of these principles. Likewise, it's going to help us solve and understand these physics principles. To my right, or to the right of those text, is three equations that will be relevant in this case. The first one being the strength of a magnetic field at any distance, not on the axis or perpendicular to the axis of the magnetic dipole, as well as the calculation for magnetic dipole, as well as a calculation to find the strength of our dipole as well. Continuing, the main purpose of this lab is to apply physics principles to find the magnetic moment of the bar. That's the first part of this lab. The second part of this lab, we're going to be assessing this magnet's strength at different locations in space, and we're going to do this both computationally and physically, so that we can make a comparison and see how well our predictions actually predict what happened in reality. So to set up this lab, it was required that we place the bar magnet at one end of a meter stick, and then rotate our phone, which has the magnetometer on it. Rotate our phone in a position where, at one axis, we're able to determine which what's the y-axis of the location of our magnetometer, as well as after that, maybe be able to find the x-axis by rotating the phone again. And the location at which those two axes cross or intersect is where the magnetometer on the phone actually is. I apologize if I say that incorrectly as well. Moving on, the actual experimental portion of this lab, we're going to move. I'm going to move my phone to different locations along the meter stick, as well as slightly off of the first meter stick, and we're going to assess the magnetic strength at each of those locations. We're going to document the distance that we took for each of those measurements of magnetic strength. So we're going to first look at where magnetic strength is equal to a certain quantity, and then jot down the distance that strength was observed at. So we're going to do it 3 times for each strength distance at 20, 70, 120, 170, and then 220 microtesla. Continuing, we're going to utilize a logarithmic model to find n, which is on another slide. We're going to also utilize this n to find the magnetic dipole moment mu. So as you can see in the top right, there's a logarithmic model that we're going to basically utilize to actually isolate n. Once we have a strong relationship between the strength of the magnetic field as well as distance, we can then isolate n just because we know it's the slope of the graph that we're going to graph. Continuing, here is the result of that the modeling between the distance and magnetic strength. As you can see, it produced the relationship that natural log of magnetic strength is equal to negative 2.5199 natural log of the radius minus our y-intercept, which is 13.678. So from this, we're able to deduce that our n is around 2.52, and then we're also able to deduce, knowing that n is equal to 2.52, that k must be equal to that very small quantity, just simply by undoing the logarithm. Continuing, we're going to utilize a computational expression to find mu. So we're going to compare this computational model and findings for our magnetic strength, which you can see at the bottom right, with our experimental findings. The experimental findings are on the bottom right of the page, and our computational findings are going to be discussed in a sec. So to actually utilize a computational method to make a prediction, we're going to utilize the magnetic dipole moment mu that we just calculated. We're also going to utilize the given off-axis formula for magnetic strength, and then we're also going to use glow script to visualize and predict that strength of the magnet. As you can see, the quantity on the left is the magnetic field produced by our magnet in reality, and then our prediction method is going to utilize this quick is going to need to utilize this quick arithmetic to find mu. And we're going to actually use this mu in our computational prediction. And in order to find mu, we set our expression with k, which is a combination of all of the constants in front of the magnetic strength times r to the power of some n, and then we're basically able to deduce what the relationship is between magnetic strength and radius, whether it's a direct relationship or if it's like a relationship with distance with r squared or r cubed. This is basically what we were able to do. Continuing, I utilized that magnitude of the magnetic moment. You can see I put down as 3.86. Then continuing through the rest of the glow script, the results of my program are displayed on the bottom. And within that text field, you can see that the magnitude of B at 45 degrees distance D, that small little purple arrow slightly above the orange ones, is equal to 3.464 times 10 to the negative fifth. So it actually ends up being a little bit smaller than the actual magnetic strength that we found utilizing the experimental method. Continuing, it's important to make some quality assumptions. We were able to make an assumption that the magnetism found within the phone app that I used for my magnetometer was actually correct. We likewise had to line up the phone to Earth's true north. This may not have been directly in the direction of true north, and that might have impacted our calculations for the strength. And you can see in the next slide I discuss what the impact of that might be. So the two discussion questions. What if you hadn't oriented your experiment to compensate for magnetic north and instead laid it out at some intermediate angle with respect to Earth? Well, that would have meant that as I moved my phone, the change in the measured magnetic strength would not change predictably, and it would also impact the manner in which those numbers change. It would make them less accurate because in order to be able to accurately assess the magnetic field of the magnet that I had, if I didn't line up at a true north, moving my phone in different directions will change the amount, like each time I change my location of my phone, it's going to unpredictably change the magnetic strength that I receive, and it would disrupt the further experiment. Likewise, if I were able to stick two identical magnets together and to end and run the experiment again, nothing much would change. The magnetic moment would increase, assuming that the two magnets were lined up in a correct manner with north and south being in the right orientations. But anyways, it would not impact much of the experiment. It might probably increase our magnetic moment that we both predict and would experimentally have found. So yeah, that is really the results of that. Anyways, that is the end of my lab, and thank you for listening.